comparable to the air pressure outside. So assuming this person is right around sea level there, so the pressure is 739 millimeters mercury here, and then the temperature okay, so in this case, what we're asking you is how many moles of air, everything combined together, a mixture of nitrogen, carbon dioxide, and oxygen. Okay, so we want you to find the number of moles. So again, if you list everything given from the question there, and you will clearly see which equation you're going to be using. Someone could be PV equals to nRT. So in this case, P is given, B is given, temperature is given. This is the n known that we're trying to figure out. So n equals to PV over RT. So in this case, when we do 739 times 3,000 and 0.08206 times 38. Right? No. R is involved in this equation. Every time that you use PV equals to nRT, you have to pay very close attention to the units there. Millimeter mercury has to be converted into ATM. Okay, and that milliliter has to be converted into liter, and temperature has to be converted into Kelvin. This is the constant there. Okay, so how do you do the conversion there? Well, 1 ATM is equivalent to 760. So if you have 739 millimeter mercury, each ATM is equivalent to 160 millimeter of mercury. Again, nothing new here, dimensional analysis. Conversion factor given, plug it in, cancel out the unit you don't want, you end up with the unit you do you want. So for this, so for each of the calculation, it's going to be a dimensional analysis, and you just need to know the conversion factor and do the conversion before you plug them in. And then if you use the correct unit, this is the answer you're supposed to get. And I urge you to do this calculation after class. Make sure you compare your answer and make sure this is what you get. 3 sig fit, 0.114 mole. So that's the total number of moles of gas inside the person's lung, okay, under this particular condition. And of course, if you go to a higher elevation, the pressure is decreasing, and well, the volume is probably going to be constant, and the number of moles of gas, depending on the body temperature there, and the number of moles of gas will start to fluctuate up and down depending on where you are, depending on the pressure. And then one of the examples that we gave you when we were talking about the Boyle's law there is that if you go down deep in the water, their pressure is increasing, so the air is being pushed out of your lungs. You have to use a pressurized tank in order to be able to breathe freely and just normally just as you were at the sea level there. Okay, so that's another type of question, and again, listing the given quantities, and then you will clearly see what you need to find out. And once you see that information there, and you can identify which equation you will be using, and the rest of it is plug the numbers into the equation. For this part, for this particular chapter, one special thing there, you have to pay close attention to the units for the quantities involved in there. So you need to make sure you are using the correct unit. For ideal gas well, whenever R is involved, pressure has to be in ATM, okay, and volume has to be in liter, and then temperature has to be in Kelvin. Well, temperature has to be in Kelvin no matter what. So that's something that you always need to remember. Now, here's another question there we can ask you there. We can ask you to calculate the volume of 1 mole of any gas, and 1 mole of gas, whether it's a mixture or an individual gas there. Under STP, how much volume does it occupy? So STP, this is the term that you need to know. STP stands for pressure equal to 1 ATM or 760 millimeters mercury, temperature equals to 0 degrees Celsius. So in this case, when we ask you, if you have 1 mole of gas, and you set the pressure and you set the temperature at STP, how much volume do we have here? So again, in this particular case, we use the ideal gas well equation we use the ideal gas law equation. So volume is the unknown. We want to find out. And STP, the pressure equals to 1 atm. Okay. Temperature is 0 degrees Celsius. And number of moles, we have 1 mole. So PV equals to nRT. In this case, we need to figure out V. So V equals to nRT over T. That would be 1 mole times 0.08206 times right? No, of course not. Temperature, you cannot use 0 degrees Celsius. I intentionally put temperature as 0 degrees Celsius in there, so you will fall into. No, I want you not to fall into the trap there. So I make a mistake on the board there. And this has 273.15 Kelvin. You have to convert it into Kelvin. So you have 1 mole of gas, gas constant, temperature 273.15, 1 atm. This number is a very important number that we need you to remember. Oops, I meant to have an L in there. So if you do your oops. Yeah, the molar volume. I thought I had the equation in there. The equation is on this particular slide. Okay, so we have 1 mole of gas, R gas constant, and 273.15, that's the temperature, under STP, 1 atm. You can see atm cancels out, mole and mole cancels out, Kelvin cancels out. The only thing left is the liter there, 22.4 liter. What this number indicates is that for 1 mole of any gas under STP, they occupy the same volume. Now, molar mass is the term that we describe the mass in grams for each mole of a particular chemical, compound, or element. Molar volume would be the volume occupied by 1 mole of any substance, but we don't use the term molar volume to describe a liquid or a solid. We use molar volume to describe gas. But when you use molar volume to describe gas, you have to specify what's the temperature, what's the pressure. So molar volume at STP, standard temperature and pressure, that's 273 Kelvin or 0 degrees Celsius. Okay. And the pressure equals 1 atm. Molar volume of any gas equals to 22.4 liter. Okay, so it doesn't matter what kind of gas you have. You can have carbon dioxide, water vapor, even hydrogen gas, nitrogen gas, and oxygen gas, whatever you have, or even a mixture. As long as you have a total number of moles as 1 mole. 1 mole of any gas, 1 mole of air, a mixture of air, a mixture of nitrogen gas and oxygen gas will occupy 22.4 liter. So that's the molar volume. Now the importance here is that the molar volume, using the molar volume under standard condition there, we can actually quantify the amount of gas that we have in here. So 1 mole of helium at STP will occupy the same volume, 1 mole of xenon, 1 mole of methane. They are all going to occupy the same volume under the specific